Hello, welcome to Picture Me Coding with Eric Aker and Mike Mull. Hi, Mike.
Hey there.
Mike, how's your life this week?
It has been satisfactory.
Oh,
I would give
mine
it a
also.
I would give it a solid B.
Solid B. I'm probably usually a B plus to your B. I took half a vacation, half a week of vacation this week, and I went snorkeling, so that's probably B plus.
That definitely is extra credit right there.
What are you listening to? Anything good, or is the music dragging you down?
The thing I've been listening to all week is probably something that you might classify as sad music. I'm not sure. So Nick Drake, I think of the two of us, you are probably the bigger Nick Drake fan. I've been listening all week to this album. I guess you'd call it maybe a reissue. I'm not sure.
Hmm.
But they put out this, what they still call a box set, even though I don't know if anybody buys CDs anymore.
It's an imaginary box.
They put out this thing called The Making of Five Leaves Left. Dick Drake's first album that came out in the late 60s was called Five Leaves Left. They recently put out this multi-disc issue of him, doing demos for the album and doing some of the recording and stuff like that. And
Mm-hmm.
it's pretty interesting. One of the things that I read about it is that since people rediscovered Nick Drake, there's been this sort of complaint that the first album was a little bit overproduced.
Mm.
There's like a lot of strings and a slightly aggressive bongo player on some of the tracks. And
That's probably true. That's probably why Five Leaves Left was never my favorite. My favorite is always Pink Moon. He just says Pink Moon, Pink Moon, Pink Moon, Pink Moon. It's genius.
I think Pink Moon is probably his best album, but I really like Five Leaves Left. I have to admit that now that I've listened to this Making of Five Leaves Left, I've started to notice some of the stuff on the original recording, which is maybe not a good thing. If you're not aware of Nick Drake, he was this, he's best known for the song Pink Moon, which you've probably heard in a TV show or a movie at some point in your life. He made three pretty great albums in the late 60s, early 70s, and then he died by an apparent suicide when he was about 26 years old.
Yeah, really young. Yeah, it's sad. Brighter Later is the other one that we haven't mentioned, right?
Right. And his music was kind of overlooked at the time it came out. And then, for reasons that I'm not entirely sure of, he was sort of rediscovered and became pretty well known and is considered to be among the great folk artists of the early 70s now.
Yeah, stuff is great. I saw a jazz magazine once and it was like Pink Moon is one of the greatest jazz albums ever. And I was like, what? This is a jazz guitar album. Jazz guitar magazine.
Yeah, Drake was also a pretty accomplished guitarist. And anyway, I recommend all of his work. But if you are already a fan, this new release called The Making of Five Leaves Left is worth a listen, I believe.
Yeah, it's hard for me. I didn't really get into it. You sent it to me, and I was like, well, I already have like ideas. This album already lives in my head. It's hard to displace it with this other version of it. Maybe I'll give it another try. Unlike you, I have been listening to a new album from earlier this year, from my favorite stand up comedian, Aesop Rock. It's called Black Hole Superette. And the theme there is like you go into one of these like little convenience stores and they sell all kinds of toxic styrofoam and stuff like that, like the awash in this culture of buying products. He's got these like really funny lines in there, just like he does on all of his albums. But I just picked out a couple for you. On one song, he says, maybe why I'm terrible with names is because I'm special at memorizing the exits during those same seconds. That's pretty good, right? You could use that defense. It's okay. It's okay to be bad at remembering names. He also says, I'm too cold. Even old man Winter won't dap the kid.
This album does not have that construction song, though, right?
No, you sent me that construction song, and I realized I hadn't heard this. I knew there was something coming out. I had forgotten about it. He has that construction song for kids. Wake up to construction on my block. I love it.
Yeah, it's a great song. And it's my kids, when they were younger, went through this phase where it was all about like backhoes and diggers and bulldozers and trucks and stuff. And this song is perfect for that. It's a very funny, catchy song, but it's also kid friendly.
Yeah, unlike most of his music, probably 99% of his music, it's kid friendly. This week, you got something hard for me, and I am likely to say foolish things that are incorrect. Listeners, you are welcome to send us email podcast at picturemecoding.com. If you hear me say something that sounds really wrong, tell me. I will mention that later on. But Mike is trying to make me suffer through saying wrong things about a pretty hard topic. What do you want to do this week, Mike?
Yeah, this episode should probably come with a warning label. We're going to delve into theoretical computer science. And so we are probably going to say some things that are wrong.
The warning label is warning, blind leading blind ahead.
This is one of those maybe do your own research episodes. But
yeah. Do your own research. Yeah.
so,
Chemtrails of fluoride and stuff. Oh.
so the reason why this came up was recently there was announced this pretty interesting computer science result made by this guy named Ryan Williams, who's a researcher and professor at MIT.
Yeah. Yeah. And there's a really, really great Wired piece about it. The Wired piece is titled The Wired Piece is For Algorithms, Memory is a Far More Powerful Resource Than Time. I will link the Wired article. It's a pretty good read, but that's a tantalizing title, right? Memory far more powerful than time.
Right. And it was hailed as a very significant result. Leslie Valiant, who is a well-known theoretical computer scientist, said something about it being the most interesting result in 50 years. In any case, it is in the field of what computer scientists call computational complexity.
Mm-hmm. Mm-hmm.
And it has to do with the trade-off between time complexity and space complexity. We are going to attempt to talk a little bit this week about that topic broadly and then try to explain in a very hand wavy way what it is that Ryan Williams proved and why it's significant.
I think that latter trying to explain, that's really going to be you, my friend. You actually read the paper. I couldn't. I read the abstract. I get like participation credit or something.
Yeah, it's not really a paper you can read unless you are already a expert in the field,
Mm-hmm.
or if you put in the work to go read the dozen other papers that it references and the dozens of papers that they reference 5 years later come back.
So this is in computational complexity theory. It's we've done other CS type of topics before, but the much more readable theoretical stuff we've done is for me much more readable. It's like the distributed system stuff I find much more readable. Like I can imagine, oh yeah, I could build that. Okay, cool. Like I feel like there's something. It's hard. It's not like it's easy, but there's stuff that's more graspable for me in those types of results. Here we're talking complexity classes and computational complexity theory. Should we do like a little bit of a background, a primer? I mean, I might be able to help there a little bit. We could do
I think
time
we
and
should
space first.
talk about some of the terminology. I think one of the things that is interesting about this particular area of theoretical computer science is that it is very applicable to day-to-day programming. So
Well,
we don't.
not all of it is. I mean, parts of it are applicable to day-to-day programming, right?
Yeah, I mean, there's obviously parts of this theory that are not stuff that come up in your day-to-day work. But I guess what I'm saying is that there are parts of theoretical computer science which I don't understand and don't know how they apply to actual building of software.
Mm-hmm.
Whereas I think computational complexity does impinge on the building of software. So I think it is relevant to the sort of stuff that we talk about on a more practical level.
Okay. All right. Well, just some basics. So complexity, they break down at the theoretical level here. They talk about different classes of complexity, and they talk about classes of time complexity and classes of space complexity. And what you're talking about is at work, we might be looking at particular implementations, and we might go, "Oh, that's quadratic or that's linear," right? You hear a lot of this stuff about like, well, I have to sort this and process this, and I've got this data, and I'm feeding it in over here, and I don't want it to be inefficient. Maybe I could go from an n cubed implementation to an n squared. If you've ever had to do one of those like hazing interview processes where you're doing those like algorithms and data structures, you probably worked on this stuff a lot. That's all complexity class stuff, right? Order n, how long does it take to run this algorithm. I think that's what you're getting at when you say it relates to the work we do.
Yeah, and formally, programmers will talk a lot about, big O notation, and we'll maybe discuss what that means a little bit in more detail later. But programmers will say this runs in order n time or order n squared time. And the idea there is that for some input to that algorithm of size n, maybe a list which is n members long or an array which is n by n elements, the algorithm will have a certain running time and that will increase based on the size of that input. All of the efficient algorithms, meaning algorithms that we can compute in a reasonable amount of time, have complexities, big O complexities that are what computer scientists call polynomial. The running time is proportional to some polynomial of the input size.
Right.
So when we say order n or n squared or n cubed, we're talking about, a polynomial like you learned in algebra.
Mm-hmm. And I always liked how they talk about these programs as, quote, easy. And then,
Yeah.
then there's stuff that takes a lot longer to compute, and those things are hard. They use those terms.
Right.
But
So I mean, the distinction is between polynomial and exponential. It's conceivable that you could have a polynomial where the highest degree is 5,000 or something like that. So it's
mhm,
going to take a
mhm,
long time to
yeah,
compute something. But
n to the 100 is still going to take a really long time. But they call
right,
that easy. It's
there's
easy.
this there's this quote though. I think the computer scientist named Edmonds, Jack Edmonds. He
Hmm.
has this quote about how the distinction between polynomial and exponential is probably more significant than the difference between finite and infinite.
Wow, that's a pretty cool quote.
So it's, that the idea of something being efficient doesn't
Hmm.
necessarily mean that you can compute it fast, but there may be things that really can't be computed in a reasonable amount of time if the input gets large enough.
And that latter thing is kind of weird to imagine, but I want to go to how they talk about this in how the like practitioners in the field, how they work on these problems. And that gets to the Turing machine stuff, right? So if you ever taken intro to CS, somewhere in there in that early computer science curriculum, they're going to have stuff on computability. We've talked about that a little bit with when Nathan came on, we talked about computability a little bit, and I did a ham-fisted attempt at talking about that. Turing machines, Alonzo Church, right? Church Turing, Gödel. Computability. What is computable? What kind of programs will you actually have a program end and produce a result for? But then they say they use Turing's result, the Turing machine, or his theoretical idea, this idea of a long tape with a machine with a write head that can write values into cells on the tape. They use that in theoretical computer science to simulate these problems and talk about time and space. And when I first started hearing about this, I'm self-taught programmer, so I was like, I got to understand a little bit about this. I thought time was like ticks on a CPU, but when computer scientists talk about it, they're talking about time in terms of simulated on a Turing machine. Is that right? Does that sound right to you?
They needed to formalize it. So, like we were saying earlier, programmers like us, we sort of tend to think of these things informally. So we think of it as the amount of time that it spends on the CPU, which we can sort of equate to clock cycles or something.
Mm-hmm. Mm-hmm.
Or we even think of it as just wall clock time. The computer scientists who are working in this area of theory have to have a slightly more formal definition of computation. And so, for them, time is how many steps does it take in a Turing machine?
Right, exactly. And there are different types of Turing machines. You can have one with one giant single tape, or you can have one with multiple tapes. Like you can imagine them all kind of stacked up on each other. And in that scenario, the Turing machine can write to any of these multiple tapes. For complexity classes with time, I think they often don't use, they use the same, the model doesn't matter that much, right? The model is whether it's single tape or multi tape. You could turn a single tape Turing machine program into a multi-tape Turing machine program, and vice versa. You can go from multi-tape to single tape. So the big thing that they talk about with the complexity classes in time is some problems are easy to solve. Easy meaning it's a reasonable amount of time to solve on a deterministic Turing machine. Some problems are easy to solve on a non-deterministic Turing machine, and they don't appear to be easy to solve on a deterministic Turing machine. This is the language that tripped me up for many, many years. So deterministic Turing machine, I guess that's probably like, like there's a set of instructions. You do this, then you do that. If you see this value, move to this cell, write this value. If your state says this, go over here, do this thing. That's deterministic, right? Like the programs we write. Non-deterministic Turing machine. What the hell does that mean? You're going to take a crack at that one?
It's all on you, man.
I think so. Here's how I've heard it described, but it's like, again, these are like imaginary mathematical constructs. These are constructs that computer scientists and mathematicians use to think about time and space, right? So we're not actually programming these things. Non-deterministic Turing machine, here's how I've heard it described. If you had a non-deterministic Turing machine, it could sort of make a whole bunch of guesses at the same time, like a whole bunch of guesses in parallel. It can pick one that works. So we're not worried about problems that can't be solved. We're really only worried about problems that are computable, right? But a non-deterministic Turing machine can kind of explore the state space that just sort of magically grab the one solution that satisfies the problem. I mean, it's always hard for me to imagine a non-deterministic Turing machine. I have trouble, like, because I think in terms of like a programmer. How would I program that? Well, I wouldn't program that, right? I mean, maybe I could run a whole bunch of crap in parallel. Maybe I'm using randomization, right?
Yeah, it's a difficult concept, and I guess it also is a purely theoretical concept. So as far as we
You mean
know,
we never built these?
We can't build a non-deterministic Turing machine.
Right. It's like saying, hey, if I had this magical thing that could try all the branching paths of my program at the same time and pick one that works, then I could solve the problem quickly. And I'm like, cool, buddy. Do you have that thing? What does that thing look like?
This is a tough concept, and it's a weird naming. People listening to this who have some experience in this field will know that we're talking about P complexity class versus the NP complexity class.
Right. Stuff that can be solved quickly and easily on a deterministic Turing machine, they call that complexity class P. And stuff that can be solved quickly on a non-deterministic Turing machine is NP. For not, people often go, oh, that's non-polynomial. It's not non-polynomial. It's you can solve it in polynomial time on a non-deterministic Turing machine. Oh, and by the way, the things that can be solved in polynomial time on a non-deterministic Turing machine, some of those things can also be solved in polynomial time on a deterministic Turing machine. But some of them, we don't think they can be. And we don't know.
The other key thing about NP as a complexity class is that if you have a solution to a problem that's in the NP class, you can verify that it's correct in polynomial time.
Yeah, that's so, true, yeah.
This is a hard thing to get to sometimes. It has sort of a real world analogy in the ideas of, like, it may be hard to figure out a homework problem, but if your professor gives you the solution to the homework problem, it's probably fairly easy for you to look at the solution and verify that it's a correct solution.
If you're in NP and you have a problem that can be quickly, easily solved on a non-deterministic Turing machine, but there's no known easy solution on a deterministic Turing machine, and there's a weird feature of some of these problems. Yeah, like you said, they can be, if you give me a solution, you just walk up and hand me one, I could pretty quickly verify that solution is correct. But there's some of these hard problems, a lot of them, that can be magically reduced or turned into another problem in the same category of problems. So NP completeness, the idea of being in NP complete is you are it, and a hard problem, it is a hard problem that can also be, and this is a weird feature of them, turned into any other hard. So you could represent that problem as a completely different problem. That's one of the things that still I find just so weird about this. You show up with a particular type of problem. What's your favorite NP complete problem, Mike? Do you have a favorite?
I do, but it's kind of cheating.
Is it? Why?
Because it's probably 3-sat.
Oh, why is that cheating? Because it's the one that you could turn everything into?
Exactly, yeah.
Oh, okay. So 3-sat's the one that famously in the paper was at the Cook-Levin theorem, 1970, 71, something like that.
I think the person who showed that these problems could be made equivalent was Richard Karp.
Hmm. I kind of like the Hamiltonian path problem because it just sort of makes sense to me. Traveling salesman's kind of cool too, but Hamiltonian path is like, hey, I've got this graph and I want to visit every node once. Like it's so easy to tell you this problem. And it's kind of surprising to me that you could turn Hamiltonian path into a Boolean satisfiability problem or one of these other generalized Sudoku is also Hamiltonian. What? Like these don't have anything to do with each other. You could just turn one into the other. That's a surprising result, right?
It's
Surprises
very
me.
surprising. Yeah, I think it's
Yeah, surprising.
probably one of the most astonishing things in theoretical computer science.
It's just so weird. It's like you're looking at this person who wants to get into the R-rated movie, and it's really three kids in a trench coat. That's how all of math works. Like what? That's surprising.
It is surprising. It's very useful.
So, okay, I guess we kind of did a jokey, informal description here of time complexity classes. You said your favorite NP complete problems 3-sat. I think mine's Hamiltonian path. Okay, so that's time. And then we go over to the next area of complexity classes, and this is space. And I have never really completely grasped it. It's like, as a working programmer, space is both more, it's like I have more intuition for it. And so this part of the when you start talking about complexity classes in space, I feel like, yeah, I get it. That makes sense. But also it's way more confusing than the time stuff. And every time I start thinking about it, it's like, what? P space encompasses what? Help me out, Mike.
Yeah, it is, I think, less intuitive than time complexity. I think the idea is fairly similar. We mentioned earlier that there's a complexity class called P,
Mm-hmm.
which, not surprisingly, indicates polynomial. Any program that can run in a time that's a polynomial of the input size is in the complexity class P.
Mm-hmm.
And so similarly, P space is something which uses an amount of storage, which is some polynomial factor of the size of the input.
But again, the people who work on these problems are using Turing machines to simulate their to do their math, right? So we're talking about
Yeah,
space, like multi-tape Turing machine space. Like you can actually imagine cells on Turing machine tapes.
right, exactly. So we think of bytes and megabytes and so forth, but
Mm-hmm.
the theorists are using cells on a Turing machine tape.
Yeah, like if I'm saying to you theoretically, how much space does quicksort take, right? And you have to like recursively uh, recurse down and you have all these different like you put the values of some unsorted list into all these different cells on a multi-tape Turing machine and you could compute, well, if you have an array then it's going to be this polynomial size, right?
That's correct. And I think people thought about this stuff more in the early days of programming where
Oh, you're saying
memory
I don't
was.
even need to think about it? That's cool.
I think there was a time when memory was at a greater, it was a greater price for memory and you needed to use it more efficiently. And so there was a time where you thought about like, how many values can I pack into this byte and stuff like that.
Oh, cool. You're saying we just throw more hardware at it. I just put a 2 terabyte SSD, like tiny thing, no bigger than my index finger in my son's Steam Deck, like a chunk of my index finger. Just throw more hardware at it. That's what you're saying. Problem goes away.
I think there's a tendency, at least now, to think, there are reasons why I need to make this program faster. For practical reasons, I need this program to be more efficient than it is, but I can just generally use more memory if I need to.
Mm-hmm.
That's not always the case, and there are certain problems which are really not solvable in memory.
Yeah,
So
no,
you,
I think that's a fair point. So similarly, there are some problems that are so hard to solve that as the input size grows, they're never going to finish, right? It's going to take longer than the lifespan of the universe to actually compute that value. And you could have the same analogy for space. There are certain problems that are going to require, as the input size grows, they're going to require so much space that you're not just going to throw more hardware at the problem. That's what you're saying, I think, right?
yeah, I think so. It's hard to come up with problems that are familiar to people that
Hmm.
have those qualities as we can with the time complexity.
So there's a relationship between time and space, though, that's also confusing, right?
One of the confusing things is that p space actually encompasses, it's a complexity class which encompasses all polynomial problems. The weird thing about it is that it also encompasses all non-deterministic polynomial problems.
That is
So
weird because it's like if it's going to take so long to compute this value that the universe might blow up, how do we know that we would have it? How can you prove that you have enough space to to compute those problems? And somebody and that's weird that you could say all of them, right? They all are computable in p space.
yeah, so all these problems, all these NP problems, which can be verified in polynomial time, are known to be within the p space complexity class, which is kind of weird.
I'll just
There
take your
was a
word for it.
there's a line in the Wired article, which I think was in Quantum Magazine first, where it says every problem in P is also in P space because fast algorithms just don't have enough time to fill up much space in a computer's memory. If the reverse statement were also true, the two classes would be equivalent. Space and time would have comparable computational power. But complexity theorists suspect that P space is a much larger class containing many problems that aren't in P. In other words, they believe the space is a far more powerful computational resource than time. This belief stems from the fact that algorithms can use the same small chunk of memory over and over, while time isn't as forgiving. Once it passes, you can't get it back.
Hmm.
The intuition is just so simple, Williams said. You can reuse space, but you can't reuse time. Whereas Williams here means Ryan Williams,
Yeah.
who we're ultimately trying to get to.
Yeah, that's the result we're talking about. Let's get to that next, but they're talking about belief here. So P space includes all NP, that's the time complexity class problems. Is that they're talking about belief? That's not proved, that's believed.
No, P space definitely includes all of NP. That is a
Oh,
known
okay.
thing.
That's a known
So
proved thing. Okay.
one of the unproved things is that P and P space are equivalent. That nobody has been able to show yet that they are distinct. Everybody expects them to be. One of the consequences of proving that they are or are not would be that it would also solve the P versus NP problem, because since all NP problems are in P space, if you prove that they are not equivalent, you've essentially solved the P versus NP problem as well.
Hmm. And
Um,
that's one of the most famous problems is the Millennium Problem. Listeners, if you can solve this problem, you can win $1 million. And there's all sorts of quackery around this. Every I used to read the computer science subreddit, and every few months someone would be like, "I solved P versus NP," and it turned out that they were just totally quacks. And I know people who are computer science professors at various universities, and I guess a common thing for them is for like people to show up and say like, "Hey, I solved this really hard problem," and they're just sort of like an isolated kind of weirdo like us. It turns out they haven't usually solved the problem. So we're getting back to space and time because the Williams result is relating to that. Let's talk about Ryan Williams. I mean, the article is interesting. I recommend you go out and read it. There's a pretty good video explainer of it that's about 20 minutes long by the Chalk Talk YouTube channel. Also pretty good. We can link those things. I guess we'll give it a shot here, though, Mike. And by we, I mean you. And by me, I will be like, what? So, memory can be reused, is the intuition here. So, it's more powerful than time. You can't reuse time. But then, how do we apply this to these results? So how do they apply those intuitions in order to get to their results? I think is the question.
so there were a few things here that happened that Ryan Williams is building on. Let me. Should I state his result first, or should I
Yeah,
go through?
yeah. Can we understand the result if you state it?
Maybe not. In his paper, he has theorem 1.1, which says for every function Tn is greater than n, time Tn is a subset. The class time Tn is a proper subset of the class space square root of Tn log Tn.
It's a
So,
proper subset, the time.
yeah, so basically, what it's saying is that the space complexity class, square root of Tn log Tn, contains every time Tn problem.
Wow, and that space that's so small comparatively, right? Square root tn log tn is a lot smaller than just tn.
Yeah, so in a sense, what he's shown is that the amount of space necessary for a particular problem is quadratically smaller, square root size of the time. And the first thing he says after stating this theorem is, "We find theorem 1.1 to be very surprising."
Yeah, there's great lines in this Wired piece where they interviewed him, and he's like, "Yeah, I thought I must have been wrong, so I put it aside for a year." He was just sort of shocked by his own result. He thought it had to be wrong, and he just kept working on it.
It's such a surprising result that, yeah, he thought he was wrong. And he took a long time to sort of work this out and verify it with other people before he published it, because it's such a remarkable improvement on the previous lower bounds that
Hmm.
it just seemed like it couldn't be right.
Okay, so build up to some of the research that he bases this on. Can you explain it to me? There's the Pebbles thing. There's the tree evaluation stuff. I have just vague notions of this stuff.
So, probably the first thing to talk about is this paper from 1975 by some people whose names are pretty familiar. So, one of the authors was Hopcroft.
Hmm.
If you have the famous algorithms book, you might know his name. And the other person on this who is pretty well known is Leslie Valiant. Valiant is a pretty well known theoretical computer scientist and has written a few popular books that are interesting to read. He's also the person who is known for probably approximately correct, which is one of my favorite computer science terms.
You got some bangers today. Infinite and finite is a less significant difference than P and NP. Or no, exponential. Sorry, you said exponential and P.
They published this paper in 1975 where they were able to demonstrate that you could use slightly less space than time. And I think the factor that they came up with in their paper was Tn over log Tn.
Hmm.
Process that they went through is very difficult to explain, but it involves this thing where they simulate a I think they simulate a single tape Turing machine with a multi tape Turing machine, but they use this blocking procedure. Paper is kind of a famous paper called On Time and Space, and it's from 75 and was a pretty significant result. So that's one thing that he built on. And then Cook, who is the same Cook who wrote the original paper in the 1970s that kind of introduced the idea of non-deterministic polynomial. He wrote this other paper that tried to determine lower bounds on the memory needed to do certain tree evaluations. And
Hmm.
again, I can't really go in, I don't understand the details well enough to explain it, but they use this interesting technique called pebbling.
Wait,
Or,
yeah, this is pretty cool. Yeah, so like if you have a Turing machine, a multi-tape Turing machine, you could sort of imagine the states that it transitions through as it's computing as a tree, right? I mean, that makes sense to us. We do that all the time anyway, that type of computation.
yeah, and you can sort of think of it as like at the particular point I'm in the computation, what state do I need from the past?
Right,
What
right.
state do I need and what state don't I need? But
What state produces this state? And the
right.
pebbling thing is interesting because it's like, what's the minimum amount of memory? Pebbles is like, if I gave you a handful of pebbles, and those were going to be the only bit like registers on a CPU that you could use to compute this tree. Those are the only ones you got. Can you do it? And their paper was sort of about like you can evaluate this tree with this minimum number of pebbles. Is that right? Do I have that right?
Yeah, that's pretty much right. So they kind of thought of this as a game
Yeah.
where the idea is that you like literally put pebbles on nodes of this tree, and then
Mm-hmm.
the idea is to get essentially to the root of the tree
Mm-hmm.
using the minimum number of pebbles.
The root would be
And
like the final computation. Like, what are you trying to produce? You're trying to compute something at the end.
right, so you're kind of trying to compute something from the nodes of a tree.
Mm-hmm. And you've only
And
got this many registers, this many pebbles in a
yeah,
bucket.
so they demonstrated in this paper, the optimal solution given this Pebble game. And at the time, this was thought to be the lower bound on the memory needed to do these types of tree evaluations. Cook offered a $100 bounty to anybody who could find something that was a better lower bound. Somewhat surprisingly, one of the people who claimed the prize was Cook's own son.
Oh, that sounds like the fix is in here, Mike. Wink, wink. I'll give out $100 to anybody who could solve this. Oh, it's my son. 6 years later.
So he wrote this paper with some other people. He demonstrated that you could use less memory to do these tree evaluations, but it depends on this very surprising and kind of hard to grasp idea of being able to reuse, to sort of use the tree node location, tree node memory as to hold different values at different times, sort of.
To
Um,
hold different values at the same time.
at
You
the
have
same
your
time, yeah.
value and you have a computation, and you're going to store those as like a single number. They're using some nutty math in here to store the computed value and like an input together. That's kind of rad to think about.
Yeah, it's a clever idea.
I mean, Chalk has a really good like how let's say you're going to swap two variables. How do you do that? Almost always, you're going to introduce a temporary variable, right? I've got an A and a B, and I want to put B where A is and A where B is. And if I take B and put it where A is gone. So I need to take A and put it in some temporary place. I take B and I put it in A, and then I take A and I put it in B. That's standard. We just do that all the time. You think about the like typical Python Fibonacci, and it's like B comma A equals A comma B plus A, right? Like there's
Yeah,
temporary variables that are pretty typical, and they're like, no, you don't actually need that. You could use math, and you could store the variable and the computed result here, and then still produce the other computed result here. And I was like, what?
right. They call this fractional pebbling in the paper, I believe, and I think there's a reference to something called squishy pebbles,
Yeah, I like that.
which
In the
is a
Wired article, the quote is, "We can actually think about these pebbles as things that we can squish a little bit on top of each other." That's a good quote.
squishy pebbles does sound a little bit like a breakfast cereal, but um,
Okay, Mike, I got an idea for you, a winning business idea. I want you, I know you're just on your own out there. You're doing some vibe coding. So here's what I want you to vibe code up for me. I want a database that uses all this super cool space saving magical math to store everything in a tiny, tiny, tiny amount of space, the tiniest possible amount of space, like on a business card. So, database on a business card. That's my pitch for you. Sounds like an Aesop
yeah,
Rock lyric, maybe.
databases for embedded systems.
Squishy Pebble databases. You could do it,
Yeah,
right?
we
Just
could even call it squishy pebble. Uh,
they might take a really long time to store data, but you know what? It's a very small amount of space.
so anyway, Ryan Williams sort of magically took all these ideas and put them together, particularly ideas from the Hopcroft Paul Valiant paper and ideas from the Squishy Pebbles paper, and he combined them to come up with this result that you could do time n problems in square root of time n over log time n space, which was very surprising and very theoretically interesting.
Here's where I get my participation credit. I'll read to you this chunk from the abstract. So he says, as you mentioned, it is shown that every deterministic multi-tape Turing machine of time complexity Tn can be simulated by a deterministic Turing machine. That's single tape, right? Of tape complexity Tn over a log T of n. So you could take multi-tape, put it in single tape. You can simulate it single tape. Our simulation reduces the problem of simulating time-bound and multi-tape Turing machines to a series of implicitly defined tree evaluation instances. There's that tree evaluation thing, leveraging the remarkable space-efficient algorithm for tree evaluation, recently found by Cook and Mertz. So these ideas, he kind of put them together. And in the Wire piece, he says, I thought I was losing my mind. Like, I must be wrong. In the Wire piece, they describe this as until now, the only known algorithms for accomplishing certain tasks required an amount of space roughly proportional to their time. And researchers have long assumed there's no way to do better. But Williams builds a mathematical procedure for transforming any algorithm, no matter what it does, into a form that uses much less space. This idea implies a second result about what you cannot compute in a certain amount of time. That part I got a little stuck on. And they quote Paul Beam from the earlier paper. He says it's a pretty stunning result of massive advance. So you can always convert it into you can convert an algorithm into a version that uses a lot less space. And you can also use this result to talk about what you can't compute. Do you follow those?
Yeah, the part about what you can't compute is a little bit more difficult to understand. What he says in the paper is another consequence is that there are context sensitive languages which need essentially n squared time to be recognized by multi tape Turing machines. I think what they're referring to is that there's this idea of certain context sensitive languages. The result that he came up with implies that certain context sensitive languages can't be decided in less than quadratic time. But that's very hard for me to understand and explain. So
Yeah, I don't have I don't have a whiff of really getting that one. I just thought it was an interesting comment on the result because and I wanted to understand more about it. What's my takeaway for this, Mike? My new goal on every single pull request I review is to say to the coder, the person who wrote it, sorry, not coder, to respond to the contributor, you know what? Following Williams' result, can you use a lot less space here?
yep, I think that's probably something you should check on every pull request is make sure.
I could just
Yeah,
make a GitHub action to comment that on every single PR.
I have profiled your code and
Following the result from Williams 2025, you should be able to use a lot less space.
yeah, anytime somebody asks for more a higher memory limit on a Kubernetes manifest, you should say, prove to me first that you need this memory.
So I'm laughing here because what we're doing ultimately is we're looking at this really cool stuff that's theoretical results at our field, and we're saying, how can we use this to be really annoying?
Exactly. I mean, which I think is really the whole point of theoretical computer scientists.
So, so I find out I hear about these types of things and I think, wow, that's so cool. It's kind of mind blowing to consider. I do you think there are practical applications here? I mean, I'm joking, but my database on a business card idea is a bit of a joke too. But are there practical applications for us, or we still have to wait to see? I would guess no. I'm not going to put you on the spot and force you to come up with one. I just do you have a gut level response like, wow, this is going to produce some interesting results in the future?
I think it probably will. I think there are probably going to be practical implications of this. I wish I were the sort of person who could immediately see what those things are. I think it's probably more likely going to have grander implications on theoretical computer science itself. Williams talks a little bit in his paper about how, maybe this process could be applied recursively and further separate P from P space. If this could be elaborated on and someone could finally produce a proof that P and P space are distinct, that would be monumental result in computer science.
Hmm.
So I feel like people are probably going to be at least exploring those avenues for many years to come.
Wow. I mean, wouldn't even hazard a guess on if these problems will eventually be resolved from a bystander. Like I'm in the stands watching the race cars go around the track here. There's a bit of a Zeno's paradox feeling of it. Like they always get halfway closer to whatever the goal is, and the goal's still so tantalizingly far away.
I just thought this was a very interesting result, and it has nothing to do with AI. So I thought that was also another benefit of this topic.
All right. Well, I enjoyed reading about this. Listeners, we will share with you a list of links to things. The Chalk Talk video is really good on this. We'll share a link to the paper and we'll share a link to the Wired article, which is also highly readable, very good, and some of the other background materials that you might find. If you have comments or questions for us, feel free to email us at podcast@picturemecoding.com. This is Picture Me Coding. Mike and I do this show every other week. And if you'd like to support the show, we do have a Patreon. Look for us under Picture Me Coding on Patreon. This has been Picture Me Coding with Eric Aker and Mike Mole. Thanks so much.
See you next time.
Bye-bye.